Alrighty. So last Wednesday, we started talking about continuity and we were able to finish that up. I had to patch in a little bit in an extension video, which is also posted on Canvas. So take a look at that, especially if you struggled with questions number 8 and 9 on the quiz. There was a supplementary video that was posted on Wednesday for that. But right now we're going to start off our third day of Math 150 by taking a look at limits involving trigonometric functions, okay? And so we're gonna take a look at two specific cases. Is the sound okay, by the way? I almost put my paper on top of my computer, but sound okay so far? Okay. Okay, so let's take a look at this graph here. So I've gone ahead and gone into Desmos and plotted f of x equals sine x over x, okay? And when you graph that, you should get something that looks like this, okay? And so my question for us is this: as we look at this picture, just from the picture and what we learned last week about limits, let's go ahead and start with the limit as x approaches negative infinity. So let's start with this one right here, okay? From our graph, what value do we think the function is getting to when we go all the way out to negative infinity? So meaning we keep going in that direction. What y value do we think the graph will get really close to? I've got one answer as a 0, 2, 3. Okay, so it seems like a few of us are thinking 0. And I'm wondering, for the folks that say 0, why do we think that is? Like, what about what we can see in the graph makes us think that potentially the y value is going to get really close to 0? Okay, Yithon says in the chat, the amplitude is getting smaller and smaller. Yeah, it looks like the waves are getting sort of like shorter and shorter, right? As we go, like if I were to start to trace this, it goes up and down and up and down. But even just the part that I've already traced, it seems to be going up and down even less, okay? And so we can almost imagine, like, here we're at an x value of negative 25. If we kept going all the way to negative 100, negative 1,000, we can maybe start to imagine that those waves would get flatter and flatter and flatter. Exactly, or it oscillates getting closer to a y value of 0, okay? And so that is indeed the limit. When we approach x, or as x approaches negative infinity, this particular function gets closer and closer to 0, okay? Now, based on that reasoning, what are our thoughts about limit as x approaches positive infinity? So when we go to the other end, if we start tracing, yeah, it looks like those waves are getting flatter and flatter as well. And so we can say that the limit as x approaches infinity goes to 0 as well, okay? Now those two are good to know, because I think what we can start to see here is that what we approach in terms of the x value is important. Like the x value underneath that LIM, that tells you where to look on the graph, okay? So let's finish up here by taking a look at this middle one, the limit as x approaches 0 of this particular function. What do we think that limit is? I see a bunch of people who are saying 1. Okay. And I would agree that the limit as x approaches 0 of f of x is indeed 1. And if we think about that, well, here's our x value of 0. And if we approach from both sides, it sure does look like we're getting close to a y value of 0. Okay. Now, one thing, I cannot zoom in on this because I'm not in Desmos, and so we won't necessarily see. But if you graph this on Desmos, you're going to actually notice that right here at x equals 0, there's a hole in the function. Okay. So there is a hole. So that means that there's not actually a value there. We can't say, if I asked you for f of 0, what would we say for f of 0? Yeah, exactly. F of 0, we would say, is undefined, or it does not exist, because the actual value, we can't get an actual value, but we can get really, really close from both sides. And it happens to be that the left-hand limit approaches the right-hand limit, which gets you to 1. Okay. And so what I like about sort of this particular picture is it allows us to practice the idea of limits, like where do we look on the graph? What are we trying to think about when we find limits? And what I really want us to connect there is that limits are the y value that things are getting really close to. Okay. Now, Ethan, I really like your comment here about things being a fraction. And we probably could have guessed from the beginning that if we put 0 in for x, that is going to be problematic, because we're saying, let's take something and let's divide it by 0. Okay. So that's a really good indicator when we're looking at the equations to say, we have a variable down there, so we might have a hole or a vertical asymptote somewhere. Okay. Really good observation. All right. So let's take this. I want you to keep this graph in mind. Okay. Let's keep this graph in mind, and we're going to start to see like what the questions actually look like when we're taking a look at limits involving trigonometric functions. All right, so we've got a few examples here, but let's take a look at example number 5. Okay, so from above, one of the important things to know is this green one right here. Okay. This is the one that gets asked about a lot. People want to know what happens when we get close to 0, okay? And so what we're going to do is we're going to use what we have and try and figure out how we can get example 5 to sort of match that same form. And so if I were to rewrite the entire expression for that green one, I would say that the limit as x approaches 0 of my function, which was sine x over x equals 1. So that's really what I'm starting to work with here, okay? Because again, sort of that middle part of the function gets really close to a y value of 1. So thinking about that, I look at this question 5 and I'm like, that looks pretty similar, right? Sine of 7x over x looks pretty similar to sine x over x. And I'm wondering if anybody has any guesses off the top of their heads of what they think the answer for number 5 might be. Okay, so you've done one small thing here. I'm not asking for f of 0. I'm not asking for f of 0. Okay, so when you say DNE, I feel like that's more of an answer for f of 0. Now I'm asking about the limit, okay? So I see a couple guesses, people thinking maybe 7, right? Now, if people think 7 is the answer for number 5, what do people think the answer for 6 is? Okay, so we have a guess of 7. Using that same idea, we have a guess of 7/4. Okay, well, let's kind of keep going here. What about these last two here? What do we think the answer for example 7 might be? I see a 4/5. Okay. Now, I think number 8 is a little trickier to answer, but let's take a look at 5, 6, and 7 so far. So we've got 7, 7/4, and 4/5. Now, I would say, yes, exactly, Aylin, that does not follow the pattern, that last one, but we'll use what we learn in 5, 6, and 7 to actually do number 8 as well, okay? But when we're looking at these three, I'm gonna say everyone who postulated a guess here for 5, 6, and 7, you are all correct. Those are the answers. Okay, we have 7 for number 5, we have 7/4 for number 6, we have 4/5 for number 7. Okay, so if you were kind of like, I don't really know, but I'm going to put out a guess, like that's super awesome. It turns out in this case that your instincts were very correct, right? But let's unpack a little bit how we might know where this answer comes from. Okay, I would say that in like Calc 2, when you see this again, you're not really going to need to go through all these steps. But for right now, I want us to think about not just getting patterns, but also developing really strong algebra skills for the entirety of this course, okay? And so let's think about if we take this limit as x approaches 0, and I start off with the sign 7x over x. What can I what can I sort of like include in here to make it look exactly like sine x over x? Like it looks almost the same, right? But what could I include in the expression to make it look very similar, more similar to the expression in the green? Mm, okay, yeah, if I could somehow get the sine x over x, right? That maybe if we had this top thing that was being signed and the bottom thing were being signed, they would be the same, okay? Now, Ethan, I'm actually really glad you said this because no, you cannot take the 7 out, right? That is one thing you cannot do. Because the 7x, that quantity, is being signed. You cannot factor a 7 out. Okay, and I want to make that absolutely clear to everyone right now. You cannot factor out something as part of a sine or cosine or tangent. Okay, so thank you for saying that. All right, thank you for saying that. But if I wanted to follow this idea of having this thing up here be the same as the thing in the bottom, well, wouldn't I need a 7 in front of that x? Like, wouldn't that make things better? Because then whatever I had up here would match whatever I have down here, okay? And so that's really the strategy that we're going for here, is how do we make that thing that is being signed be the same as the thing in the denominator, okay? So let me get rid of that highlighted right now because 7x is not the same as that denominator, okay? But we can multiply by 1, as we've done last week. We can multiply by 1 pretty much anytime we want to, and we're not changing the actual expression. So wouldn't it be handy if we had in the bottom here a 7x. Because then this 7x on the top matches that 7x on the bottom. Then I can use that thing in the green. Okay. Well, if I have a 7x in the denominator, and that's all I have, I've changed the problem. Exactly. So I need to make sure I'm not changing the problem. So I need to make this be the same as 1. Okay, that's why I need a 7x on the top as well. And so now let's take a look at this. I've taken my original question. I've multiplied by 1, so I haven't changed anything. But the way I chose to say 1 meant that I have the thing that's being signed, that 7x, is now the same as the denominator. Okay. Now what that gives me is this. The limit as x approaches 0 of sine 7x over 7x this is the purple one, times, I'm going to keep that top 7x over here and move that original x over there. So I've got 7x over 7. Okay. Now, check this out. I'm going to leave this part as it is. 7x, 7x. But this right here, 7x divided by x. What is another way that I can write 7x divided by x? Yeah, I can write it as 7, right? And I can write it as 7 because the x is reduced to 1. Okay. Now, there's sort of some special things with constants, okay? So I look at this whole problem and I see a constant and I'm multiplying. Now, in this case, Ethan, and not only you, but specifically because you asked earlier about the factoring out, in this case, this 7 is just multiplying everything. I can bring that out to the front. So I can write this as 7 limit as x approaches 0 of sine 7x over 7x. Okay. Now, this limit, when I have sine of 7x over 7x, that is the same thing as saying sine x over x. Because I'm signing something and I have that same something in the denominator. So this whole limit is equal to 1. And so what I have is this question is really saying 7 times 1. And that is how we get the 7. No, you were wrong. You cannot factor a 7 out of a sine 7x. That is conceptually fundamentally wrong. It's incredibly tempting though, and so many people want to do it, but you cannot.
Professor, I have a quick question.
What's up?
I think I just missed this. Can you please explain how you went from the limit to 1? I think I blanked when you were explaining it.
So when we have the limit of something, of sine something over something, that's always going to be 1.
Oh, okay. It was there the whole time. Thank you.
You're very welcome. Okay. Now I know some of you are sitting there being like, well, I already knew the answer was 7. I don't understand why she's making me show all this work. I'm not going to pay attention and just not show work on the exam. And I'm going to tell you right now that that is a bad decision on your part, because I will want to see your thinking around this. Okay. So it's really, really important that you can follow the steps here, that you can make sense of what's happening. And if you did factor that 7 out at the very beginning, even if you got the correct answer, you would not get that question correct. Okay. I just want to make that really clear here. Our goal here is about matching a particular form and not just using shortcuts that maybe are not mathematically sound to sort of get there faster. Okay.
Professor, I had
Yeah.
a quick question.
Okay.
So when we see these x values, is it implied that they're in radians?
It actually doesn't matter.
Okay.
Whether
Because I'm trying on my calculator and with degrees it doesn't work, but with radians showing like those values that we're getting.
for which part?
For both sine x over x and sine 7x over x.
It's working in radians, but not in degrees.
Right. That's why I was asking if they're implied that it's in radians.
I mean, most of the time we're working in degrees. I mean, radians. You hardly
Okay.
ever in degrees anymore. Maybe a little bit for some like application things, but in general, we're looking at radians.
Okay. And then so then for like your test too, should we just they're implied that's in radians, the values?
It's a decision you'll have to make depending on the context of the problem. So if the question looks like this, then yes, you would be using radians. But in some questions we see later on this semester, it's going to be implied that it's in degrees.
Okay.
Okay.
Thank you.
All right. So let's try number 6 using the same idea. Okay. But what we're going to be looking to build here is if at some point I could find sine 7x over 7x, that would allow me to use this rule, okay, or this picture. So what I need to do in number 6 is similar to what I did in 5, where I need to find a denominator that is 7x, the denominator that matches the thing that I'm signing, okay? And so if we think about that, we're going to have the limit as x approaches 0. Let's write out our initial problem. We have this part here. I want to be clever about how I say 1. And so what are our suggestions for what I should multiply by in the purple here? 7x over 7x. Yeah, let's try it. 7x over 7x is 1. So I haven't changed anything, so that's good. And I was able to get that 7x in the denominator that I need. That means that because everything is multiplied, I can sort of switch where the denominators are. Now the 4x goes here, 7x goes up here. Okay. Now 7x over x, well, that reduced to 7. But 7x over 4x, that reduces to 7/4, right? These x's reduce to 1, and I'm left with 7/4. This gives me the limit as x approaches 0, sine 7x over 7x times 7/4. 7/4 is a constant. It is not being signed, so I can factor it out to the front. And then 7/4 stays. this is exactly the thing that I knew is going to 1. It's a value I know. So times 1, which gives us that answer of 7/4. Okay. So it's totally fine to look at question number 6 and say, I know the answer should be 7/4. You know that answer equals 7/4. Now you have to show me how you got there. Okay. You should know, okay, yeah, my guess was correct. I know it's going to be 7/4, but you should also know how to get there. All right. All right. Well, let's take a look at example 7. Okay. So example 7 here. Well, we are looking for our sine of 5x. Okay, so that means at some point I need a 5x in order to be able to use this rule. So let's see, limit as x approaches 0 for x over sine 5x. And what should I be multiplying here? What is our fancy way of saying 1 that might work? Yeah, 5x over 5x sounds good to me. Because here is the 5x that is sort of on the other side of that fraction line. Okay. And so if we rewrite some things, we get 5x over sine 5x. There's my matching pieces in the same expression, times 4x is on the top and 5x is on the bottom. Okay. Now, this right here, 5x over sine 5x, is a reciprocal of what we had before. But our limit before was 1. So when we think about the reciprocal, it's still going to be 1. Okay. And so we can leverage that to say this part, we can reduce these x's in that expression. And that's where that 4/5 comes from. Same thing, 4/5 is a constant. 4/5 is not being signed, so I can bring that out to the front, or I can factor it out. And the expression that I have left well, that goes to 1. And that is why we have an answer of 4/5. Okay, so 3 questions that are sort of similar in flavor, using that idea that the limit of x approaches 0 of sine x over x is 1. Okay. Using our instincts, being able to sort of guess these answers, but then sort of the work for ourselves is figuring out how do we confirm that that answer is indeed correct. For those of you who, I think most of you did choose to skip number 7 on the quiz, I would maybe go back to number 7 at some point, and just use that as a little bit of extra practice before the exam next week. Okay. All right, let's do one more problem here. This number 8, which is the one that looks similar but slightly different. Okay. And so what are our thoughts in terms of rewriting things? Because a lot of what we're doing in calculus comes down to being able to use a lot of the algebra we've learned before to maybe rewrite things and therefore be able to solve some problems. So what are some maybe like algebraic strategies that are coming to mind when folks look at example number 8? See a factor, okay. So what would you factor? The denominator, okay. And so we get sine 3x And when we factor that x, we'll get 5x squared minus 4. Okay. I think that's a good first step. Now, what might be really helpful here is what happens if we did this? Sine 3x over x times 1 over 5x squared minus 4. Right? Most of the time we are so used to combining fractions, but I think a really useful skill is to be able to also uncombine fractions, right? Because by uncombining them, what do you want to do to help this one out? That's sine 3x over x. What could we do to turn that into a form that's something we know the limit of? Yeah, and be a little bit more specific, not just 3x, right? We want it to be 3x on the bottom, but yeah, exactly. We multiply by 3x over 3x. So let me go ahead and multiply that on the end, right? We're multiplying by 1, fancy way of saying 1. And if we reorganize what we've written, we have sine 3x over 3x. That's good. We know how to handle that one. Times, we have a 3x in the numerator over x. And we could combine these two if we wanted, or we could leave them as 3 separate expressions for right now, okay? But now I think those first two become a lot more familiar, right? This part, we know that's going to go to 1. The second fraction, the x and the x will reduce. We're going to end up with a 3. And then the third one, well, nothing reduces from that. So now let's kind of rewrite what we have. The limit as x approaches 0. Okay. What do we have left in the numerator? We have a 3. Good. And what do we have left in the denominator? Yeah, exactly. 5x squared minus 4. Okay. Now, let's substitute and see what happens. 3 over 5 times 0 squared minus 4. And so we'll end up with negative 3, 4. Okay. And if you graph this particular function on Desmos or whatever graphing tool you have, and you zoom in to where x gets really close to 0, I bet you're going to find that the y value gets really close to negative 3, 4. Okay. So the moral of the story here is that we really, really need to be thinking about algebraic strategies. So things that get highlighted during different lessons might come up in current lessons, and that's sort of a flexibility we want to start to have. Okay, Ethan, what was your question?
I was going to say in example 8, where we multiplied in the second step, 3x over 3x, we did that.
Mm-hmm.
I actually thought of just multiplying 1 over 5x squared minus 4 by 3, which comes out to the same thing with less work.
Yes, you could do that.
Would that be fine on the exam?
Mm-hmm, because you still get that 3 over 3, which is still 1, right?
Okay,
yeah.
Thanks.
Mm-hmm. All right, so this one right here, this is the main trig function that folks like you to know in terms of limits. This is a good graph to kind of internalize that it sort of looks like a cosine graph, but that the ends get flatter and flatter and flatter, and that the middle gets really close to 1, okay? And knowing what happens at the left end and the right end and in the middle are sort of things that come up again and again, okay? The second one that we're going to do today is a little bit less common, all right? But it is one that I think comes up occasionally, so I just want us to have a little bit of exposure to it, okay? So the second one, let's take a look at this function, all right? Cosine x minus 1 over x. And so this graph, if you graph it, looks something like this. And let's see if we can use our graph to figure out our limits, just like we did before. Okay, the left end behavior, the right end behavior, and the middle. The left end behavior in the black, the right end behavior in the blue, and what's happening in the middle in the green, okay? So let me give you a moment to just look at your graph, see what you think. And then I'm gonna ask you to type in 3 numbers, okay? The first number is going to be what you think happens when you get to negative infinity. The second number, you're gonna type this all together in like one answer. The second number is what happens in the middle, that green part. And the third number will be what happens at the blue one, which is what happens when we go to the right-hand side, okay? So you're gonna type in 3 numbers. Give you a moment to do that. What happens at the left end, what happens at the right end, what happens in the middle. All right. And if everyone could go ahead and hit enter, let's see what you have. Everyone should have 3 numbers in their answer, 3 numbers. All right, 0, 0, 0, 0. Okay, so no matter where we look in this particular graph, these 3 key points, like the left end, the right end, and the middle, this graph happens to go to 0 at all 3 of those locations, okay? And we can tell this left end because we can see that the waves probably get flatter and flatter and flatter. If we go to the right end, I bet those waves are going to get flatter and flatter and flatter. So they get closer to a y value of 0. And in the middle, we do have a hole here, but from the left-hand side and from the right-hand side, it gets close to a value of 0, okay? Now we would say, just like we did for the previous one, f of 0 is undefined. So there's no actual value there, but the limit gets close to the same number from both sides, okay? So if you're sitting here and you're like, I can confidently look at a graph and tell you what the limit is, that's a really good place to be. That means that you really learned how to read limits from a graph last week, okay? And if you're not quite there yet, that is a great thing to ask about. Come to office hours, go to tutoring, whatever it might be, but it is an important skill that we want to have, okay? So let's take a look at example number 5 here, okay? So example number 5, well, I see that the top half, cosine x minus 1, kind of looks like this graph that we just looked at. But what do I wish were in the denominator instead of sine x? Like if I had something else in the denominator, I could answer this question immediately. Yeah, if I had an x down there, right? Well, I can't just get rid of that sign. I have to use the same idea that I've been using, which is how do we use a fancy way of saying 1 to create something more similar? And so this time we're going to multiply by x over x. Okay, that's our fancy way of saying 1 here, precisely because, as these 3 folks pointed out, we wish that that denominator were 0. That would make our life much easier. And so we have the limit as x approaches 0 of cosine x minus 1 over, let's bring that purple x over, times sine x is still in the denominator and the x is in the numerator. Okay. Now we've actually managed to match not just one, but pretty much two things here. Okay. What do we know about this? What is this going to go to? Cosine x minus x over x, if I'm going to x approaches 0. Yeah, this value, as I think about the graph right here, is getting really close to 0. Cosine x minus 1 does not equal sine x. But if you were gonna say have some squareds in there, I bet you could make that happen, yeah? Okay. So this is going to 1, okay? Or sorry, not 1, 0. What does this one go to? Yeah, really nice. So this actually is asking you, what's 0 times 1? And just because it's Monday morning, let's make sure we all know 0 times 1 is going to give us 0. Okay. And so if you were to type in cosine x minus 1 over sine x, and you looked at the graph as it got really close to 0, x equals 0, you would see it gets close to a y value of 0 as well. Okay. There. Let's try the next one. I did not number these correctly, huh? Okay, well, here we are. All right, let's take a look at this one. Well, what do I wish could be different about example 6, other than not even being a problem? How could I make this look like something that I know? Get rid of the 7s, okay? How could we get rid of those 7s? Seven minus 7 divided by 1. Where are you getting that from? Okay, multiply by 7x over 7x. Yeah, that's 7 minus 7 times cosine x. So I don't know what you mean by it's subtraction you can't factor. You can absolutely factor here. Okay, so as we see here, we've got a 7 here. And then there's a 7 times something else. And we're separated by, yes, we're separated by a subtraction sign. So you can 100% factor out. And you get 1 minus cosine x. And then all over x. Okay. Now, I do want to go back. I noticed that someone said we multiply by 7x over 7x. That's mathematically valid to say 7x times 7 or divided by 7x, right? And we're multiplying by 1. But we want to be really thoughtful about like what's helpful here. And so because the cosine is only cosine x, not cosine 7x, I don't want to introduce a 7x into there, okay? But I don't want 1 minus cosine x, right? I'm almost, like I'm taking one step in a direction that's getting me closer to what I want. but I still have 1 minus cosine x, and that is not sort of what we have here, right? Here we have cosine x minus 1. Winner, winner. So that -1, right? We talked about this last week, and it was, I don't know, sort of like a weird trick that maybe we hadn't seen that much in our algebra before. But cosine x minus 1 is so, so close to 1 minus cosine x. And that is exactly what we need to do here, in that we need to say, I also want to factor out a -1. And that will make the inside become exactly -1 plus cosine, or I'm going to write it as cosine x minus 1, okay, over x. All right, so now what do we know about this? This is going to approach a y value of 0 as long as we're looking at x gets to 0. And so this question really is -7 times 0 is what? And that gives us 0. So I think this is actually a really good example of what makes calculus tricky. I think what makes it tricky is there's so many little algebraic strategies that at some point you learn, but then it's like, oh, I have to use that again? And like, yes, you have to use that again. Okay, so definitely pay attention to these little things. I try and pick problems that have things that come up frequently, like that -1 trick, okay? But it's not guaranteed that we're gonna hit all of them. So let's just make sure that we're at least paying attention to those sort of algebraic strategies here, okay? All right, we got 2 more questions here. These ones are a little bit more of a throwback to trigonometry. Okay, so we're going to use a little bit of what we learned with the previous ones, but we're also going to look at like some old things we learned from trig. So my first reaction when I look at this question, limit as x approaches 0 of x cotangent x. I'm like, what? That sucks. She just talked about sine x and cosine x. She did not talk about cotangent x. How am I even supposed to do this question, right? Totally valid. But we learned a lot of identities, right? And I don't mean like the bazillion identities that you learned like later in trig, but some of the earlier identities, some of our more basic identities, I think become really helpful in these last 2 problems. I think we could do 1 over tangent x, but I think there's one that might even work a little bit better than that one, okay? Yeah, I'm gonna say cosine x over sine x. Only because we learned about some stuff with sine x and cosine x. We haven't actually learned how to do this with tangent, right? So 1 over tangent is absolutely mathematically valid, but maybe not as helpful in this particular case. So if we rewrite this, we have x, let me do this, x over 1 times cosine x over sine x. Okay. Now that I've turned cotangent x into cosine x over sine x, how can I rewrite the thing I'm taking a limit of to maybe match with some identities that we've learned? Exactly. So we could say x over sine x, and then that would leave us with cosine x over 1. We know that this part goes to 1. And then we're really thinking cosine of 0. And what does cosine of 0 equal? It equals 1, okay? And so for those of us who maybe those trig values have fallen out of our heads a little bit because we didn't have to use them all over winter break, I would, make sure to brush up on those a little bit more. It tends to be like 0 and pi over 2 a lot. Those values come up a lot, but sometimes the other ones do as well, okay? All right, one last question here. What might we want to do to example 8? Like, how might we want to rewrite it so that we could start to think about structures that we've learned today? Okay, sine x over cosine x, right? Let's think about this tangent as things that we know. And those things that we know tend to be sine and cosine, okay? So I could write this as sine x over cosine x. That's that whole green part. And then I have that 3x on the bottom, right? All right. What do I need to do here in order to use some of the things that we learned earlier? How do I make this look like one of the other things that we've done before? Okay, so you want to make it look like a sine x over x, okay? Yeah, having an x over x would be great. And maybe we could just do this. Everybody see what just happened there? Right? Because I could write this whole fraction as one big fraction, sine x all over cosine x times 3 times x. And I can split up fractions that are multiplied however I want to. So I can just say, let me grab these two, sine x over x. I'm going to write that as one fraction. And then I'm going to separately write the other one as another fraction. Okay. So because we're multiplying here, we are allowed to do that. And now we can say, hey, I know this sine x over x goes to 1. So really, I'm concerned about the limit as x approaches 0 of 1 over 3 cosine x. We can factor out that 1/3 if we want to, or we could say, hey, I'm just substituting at this point. Let's see what we get. 1 over 3 cosine 0. That's 1 over 3 times 1, or 1/3. Okay, so if you want to factor that 1/3 out, that is absolutely fine. You'll get 1/3 times 1, and you'll still get 1/3. Okay. All right. So folks, that brings us to the end of limits day 2. Okay. I know we didn't get to this part last week, but I think that this is a good review in terms of like algebra and like dipping our toe back in the water of trigonometry and all of those delightful things. Okay. So are there any questions so far about limits day 2 or any of this trigonometry stuff that we just talked about?
Yeah, I have a quick question. So with each exercise, as we approach the end, like as we get close to the end, you just take the limit out. You don't write limit x as it approaches 0. So when we reduce something to 1, that's not what f of 0 is. That's what the limit is as it approaches 1.
Correct.
Okay, so limit as x approaches 0.
Mhm.
Okay.
All right. Any other questions right now? It's okay to have too many questions to formulate right now, but if anybody has a question right now, I'm happy to take it. Yes, so I skipped over that step, but if you do plug in 0, you're going to end up with 0 over 0. Okay. I think for the first exam, I would like us to just plug in numbers and see. Okay. I think for this first exam, beyond that, I don't know that we'll really need it that much. It's something to keep in mind. Okay. Because sometimes what I see is like folks don't substitute when they could have, and they end up making the problem a lot more complicated than it needs to be. So in a sense, like you should at least mentally try the substitution and convince yourself you get 0 over 0, and then that's why you have to do all the other stuff. Does that make sense? That's fine. Convince yourself that you have to do the other work, right? I'm going to answer that question right now. Okay, so let's stop sharing the screen right here. Okay. So I would encourage you to go back over these, even though it was only one question on the quiz. I think it's valuable just to make sure that you understand this process, okay? Again, that first case, sin x over x, comes up a lot. The second case, not so much, but I think it's a handy one to have at least seen one time, okay? All right, so announcements for this week. I have a bunch of announcements, and we're gonna take a break. So exam 1 will be next week. All right, exam 1 is going to be next week. Exam 1 will look a little bit different than exams have in the past if you've been in my class before. Okay. So let me go ahead and share my screen real quick. Okay, does everyone see my Canvas page? Yeah, okay. So by now, I think we all know what's happening under the logistics section. That part's not changed, but you'll notice if you go to Unit 1 limits that there's a new link here. Okay, so this is the exam 1 topic list. I'll leave you to click on that on your own time, okay? But I do post a topic list for each exam that you have, okay? And so I would encourage you to really use that to help guide your studying. I do not give out practice problems or a practice test like maybe other instructors do, but I feel like if you understand the flavor of lecture and the flavor of quizzes, that the topic list should be pretty beneficial, okay? So a few things that are different from exams from last semester, okay? And if you were not with us last semester, then this is just how exams are gonna be. So our first exam will be next week, okay? It will be on Friday, so it is not during class time. I'll post this in the announcements as well in this week's La Semana, so you'll have a reminder of this again. But the exam 1 is going to open at 9:30 a.m. on Friday next week, so Friday the 19th. It will close at 9:30 p.m. You have 12 hours. Within that 12 hours, once you open that test, you have 2.5 hours to complete the test, okay? Now, once you open the exam, you're going to find a PDF. So kind of like how when you open the quiz, there's a PDF and you get to like download it or print it out or just see the questions, okay? So once you open your exam, you'll see a PDF. It will be sort of formatted similarly to a test, like or to the quizzes. There'll be a place for you to write your work, et cetera, okay? I know that not everyone has like a tablet or a printer. I understand that. If you have access to those things, then you can download the work, write on it, or print it out or write it on your tablet and re-upload it, okay? If you do not, you can just write your answers on a separate piece of paper. That is totally fine. There's no judgment. I don't want you to feel like, oh, it's not like, you know, doesn't look as pretty or whatever. Like, I'm not judging you on that quality of, you know, your handwriting or anything. But either way, you're going to be submitting one single document for your work, okay? If you submit multiple files, I will only look at the first file. Please do not submit work with multiple files. That is the best analogy I have is like, that's if you turned in 10 pages of work without a staple attached and you just gave me 10 random pages, that's what it feels like on my end to grade multiple files. Okay, it doesn't feel good. I would prefer it so much easier for me if you just have one file. So what's different for folks that were with me last semester, you'll notice that last semester you had one question, you had to answer that one question before you could move on to the next question. I think there's a time and a place for that. I don't know that Calc 1 is necessarily the time and place for that. Only because I think with the content that we're doing, we go back and forth between so many different questions that sometimes we need to think about another question before we can do one, okay? Now this is what we're gonna do for exam 1, and I wanna make this super, super clear here. If there is cheating, you download my exam, you post it to the internet, you ask someone for solutions, you copy those solutions, we will 100% change the format of the exam. Okay, so this is like a, let's try this out. If there's a problem, we will change our testing policy for all the other exams. Okay, so I hope you encourage each other to stay accountable to being honest about your work and where it's coming from. I did want to talk very briefly. Some of you saw that there was an assignment that was the download upload assignment. Where did that go? And some of you answered that one. This download upload practice, okay? All that was just a practice to what it looks like to take, what it's going to feel like when you say, take my exam 1. You click on this, a document will pop up, you'll be able to print it out, write on it or whatever, look at the questions, and then upload your document. Okay, so this is just a practice of uploading and downloading your work. Okay, but also when you submit your quizzes, that's practice too. You do not have to do this assignment. If you did, that's awesome. But really it's just for practice, uploading and downloading documents for an exam, okay? Are there any questions about exam 1? Okay, good question. So exam 1 will be open notes, okay? I want to be very clear about what I mean by open notes. Open notes means open notes from this class. It does not mean open internet. That is cheating, okay? Open notes means the notes that you wrote for this class or notes that I posted on campus. It is not, let me search the internet for this question and it's kind of open notes, so that kind of means open internet, okay? That does not fly with me 100%. You want to know the fastest way to get me angry is to cheat on an exam, okay? So yes, it is open notes. Now, Yitan, to your question earlier about a reference sheet. So that sort of leads into the next thing that I want to talk about, which is extra credit, okay? So exams are open notes. You still have a time limit, and you'll have to make sure that you are able to finish that exam during that time limit. If you have a time conflict, come talk to me and we'll work it out on a one-on-one basis, okay? So just maybe check in with me after class. We'll talk about that. Okay. Now that actually, so I randomly chose 9:30 to 9:30. Are there other people for whom this time frame really, really doesn't work? Like all day Friday? Okay. All right. So if you, yeah, for folks who have like a regular conflict, come check in with me and let's talk about that. You can send me an email or hang out after class. Okay. Okay. Okay, so extra credit opportunities. There are 3 ways in which you can earn extra credit over the course of the semester, okay? There's a cap to it. You can't earn more than 50 points. 50 points works out to be about 5% of your overall grade, okay? So you can't earn more than 50 points, but one way that you can earn extra credit is if you come to office hours and you talk to me. So if you talk to me about math during office hours, you can get a point. If you come to office hours and hang out and never talk to me, that's fine, but you don't get the extra credit points, all right? So we're ramping this up a little bit. You have to come and you have to talk to me about math stuff. That's one way that you can earn extra credit. Another way that you can earn extra credit is by attending tutoring sessions. So ESOM has 2 tutoring sessions per week. If you attend one or both, you can get a point every time that you attend. You do not have to stay for the entire time. You just need to show up, talk about some math, and then that's it, okay? The last way that you can earn extra credit is on the exam. So on the exam, it is open notes, all right? I think we have a lot of content that we need to digest, and the semester goes by much more quickly than maybe we think it does. But if you want to create your own reference sheet, okay, I know a lot of you actually said that was a helpful thing to have as part of your studying process, okay, is that if you have a reference sheet, so it's a 1-pager, it is maybe a summary of formulas or examples or definitions or pictures or whatever you think might be useful from that unit. If you distill that down to 1 page and you submit that with your exam, that is potentially another option for you to earn extra credit, okay? So 3 ways of earning extra credit. I'll keep track of those throughout the semester. And then at the end of the semester, I have a column for extra credit points, and then I enter all that in then, okay? Yes, so the exam is due next week on the 19th. It wasn't really in this week's La Semana because it's not until next week. I will talk about it more in this week's La Semana, okay? But it'll be the 19th of February. Okay. All right, 3 more announcements and then we'll go on break. First, we did some Desmos activities last week. Overall, did people find them helpful or not helpful? It's like a quick yes or no in the chat. Okay. With the, okay, yeah, I know. There's something about just being able to move things that I feel like helps at least me visualize things. Okay, second part of that question. Do we like having the Desmos activities in class, or would we like it to be like, hey, here are some Desmos activities for this week, check them out on your own time, and I just send you the link? So in class or out of class? Okay, okay, cool. Yeah, I felt like last week I like spent all of January thinking about Desmos, and I was really excited to use all these activities, but it felt kind of weird in class. And okay, yeah, maybe we can sort of mix and match, and that way it won't take away from class time. Okay, cool. Okay. Overall, how is class going? I got like a too fast option, like, oh, too fast, too slow, just right. Like, how are we feeling? Okay, just right, a little slow, content with the pace. Okay, okay. And I know some people didn't respond, so if you have a secret response for me that you would like to share with me later, please don't hesitate to share that with me. I think it's important that like, it's not just the people who say it's going fine, that it's fine, but like, if there are people who feel like it's going a little bit fast, like that's important to know as well, okay? Okay, okay, fair. It's a fine balance there. Okay, last announcement for today, and then we'll go on break. So Wednesday's class is actually going to be a pretty grown-up math kind of day. We're going to be looking at some theorems and things like that, which is a little bit different than maybe how previous classes have been, depending on your instructors. So I think that in general, I think it's helpful to sort of like read over the textbook or something before class, but I would actually really encourage you before Wednesday's class to either read the textbook, like the corresponding sections if you're a textbook reader person, or look up some videos about those topics and watch them before Wednesday's class, okay? So I would encourage you, especially because Wednesday is going to be a little bit more grown up, that maybe like watching a video or something like that would be helpful before lecture, okay? All right, well, let me